Hey guys, welcome to Chapter 17. Just a bit of a warning, Chapter 17 is probably the hardest chapter in AP Chemistry, but we will be treating it individually. We won't do it with another chapter, it'll just be all by itself, so that's going to make it a little easier to swallow. Let's go ahead and get started with the common ion effect. The common ion effect is just another way of describing Le Chatelier's principle. It says whenever you put an ion into a solution that has that ion in it, it shifts the equilibrium away from that ion. So the substance's ionization is actually going to be decreased whenever you put another ion in there, the same ion in there, that causes the equilibrium to shift back. So, for example, what this means is if you have an equation like this one, you have the ionization of hydrofluoric acid, and you dump in some sodium fluoride. Dumping in sodium fluoride is the same thing as dumping in fluoride ions. So, basically, you're increasing fluoride ions, which shifts the equilibrium to the left, which causes more hydrofluoric acid to be formed and causes the ionization of hydrofluoric acid to be decreased. Now when you do this, since the amount of hydrogen ions actually goes down when equilibrium shifts to the left, that means the pH is going to raise. It's going to be higher than it was if it was just a pure solution of hydrofluoric acid, because we're losing hydrogen ions. If we look at another example right here, with an ammonia solution or ammonium hydroxide solution, if I dump in some ammonium chloride, it's the same thing as dumping in extra ammonium, which again causes a shift to the left in this reaction. This time we're reducing the amount of hydroxide ions, and so our pH is going to decrease because we're losing hydroxide ions. Before we were losing hydrogen ions, which caused our pH to raise. Now we're losing hydroxide, causes it to go down. So let's take a look at an example of an equilibrium problem when dealing with an ion added to an acidic solution. Here we have some acetic acid and sodium acetate solution. It tells us we have 0.3 moles of the acetic acid, 0.3 moles of the sodium acetate. And I want to know what is the pH of this. We start these out the same way as we started all the others, with a balanced chemical formula, an ice table, and equilibrium expression. It's the same thing that we did before. So I'm going to start with my balanced chemical equation. So the equation is going to look like this. Now this is one of the first things that students will get confused on, is they'll ask, well, where's the sodium acetate? Now remember, the sodium is just a spectator ion, and so it really doesn't matter. That means the only part of sodium acetate that's important is our acetate ion, which is right here. So this is the sodium acetate right there. Now if you take this and you set this up in an ice table, something that you're going to see is that now you have an initial concentration of the acetic acid, but you also have an initial concentration of the acetate ion as well. They're both 0.3 molar because we have a 1 liter solution. So 0.3 moles divided by 1 liter is 0.3 molar. Since your hydrogen ion, you have 0 of it, that means that this reaction is automatically going to move towards the right. It can't move towards the left because there's no hydrogen, so it has to move towards the right. So that means this is going to go down. The acetic acid is going to go down, while the hydrogen and acetate ions are going to go up. Now one important bit of information that's missing here is we really need a Ka value, and I didn't type it in here. I probably should have, so I'm going to go ahead and just write it in, look it up and write it in. And then I go ahead and put these numbers in, our equilibrium values, and I plug them into my equilibrium expression. And when I go ahead and do that and solve for x, I get x to be equal to 1.8 times 10 to the negative fifth, which is equal to my hydrogen concentration, which means I can use my negative log equation to solve for pH now. Alright, let's take a look at our homework problem 1985 from page 6. There's a typo for hydrozoic acid. It says NH3. It should actually say HN3 there. Now on part A and part B, these are just review questions, writing an equilibrium expression and calculating pH of a weak base. We learned how to do this in the last couple of chapters, so why don't y'all go ahead and pause this, try letters A and B, and see how you do. On letter A, we should have gotten this equation here and this equilibrium expression. For B, we should set up an ice table, which will look like this. Set up an equilibrium expression and solve for X. And if we go through and solve for pH, we get about 2.93. Now the next part of this, part C, is where we start getting into the new stuff. We're going to add a salt to this, NaN3, and we're going to see what the pH is now. Now to do this, we start out with the same equation, exactly the same as before, because remember the Na, our spectator ion, isn't really important. It's just the N3 that's important there. Now the molarity of the acid still starts out the same, 0.05 molar, but now since we're adding the salt, we have to add the molarity of N3 to this that's equal to the amount of salt that we added. So we've got mass of salt here. We're going to have to change that to moles, and then we're going to use that volume there to figure out our molarity. So I'm just going to go down here and do this. So I'm going to change grams of NaN3 into moles by using the molar mass. And I need to change this to moles of N3 negative, which is just one NaN3 has one N3 negative in it. And I get about 0.0123 moles of N3 negative. I need to divide this by the total volume, which is 0.15 liters. And I get 0.082 molar. And this is the initial value of the concentration of the N3 negative in my solution. Now the initial concentration of the hydrogen ion is 0, so this is going to move to the left. To the right, because it can't move to the left because it doesn't have any hydrogen. And my equilibrium values are going to look like this. And I have my Ka, so I can plug this into my equilibrium expression. And I get an X value of 1.7 times 10 to the negative fifth, which will be equal to my hydrogen concentration. I can plug that into my pH equation, and I get a pH of about 4.77.